Why would you choose a silicon carbide MOSFET? Well, maybe you're interested in lowering your BOM and your overall manufacturing cost. Maybe you're intrigued by improving your power efficiency and finding an easier way to meet power efficiency standards. Maybe you want to increase the power density of your design. Or maybe they're just cool, right? Well, not all of them are really cool. Yes, we're talking about Infineon's silicon carbide CoolSiC MOSFETs today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Nick Powers from Infineon and I explore the benefits of Infineon's silicon carbide CoolSiC MOSFETs. We also explore how this solution improves thermal performance with the addition of the .xt advancements, the benefits of topside cooling, and how you can use Infineon's CoolSiC MOSFETs in your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Infineon. Hi, Nick. Thank you so much for joining me.
Hi, Amelia. Thank you for having me. I'm excited to talk about silicon carbide today.
Excellent. Okay, and that's exactly what we're talking about, improvements in silicon carbide. But Nick, before we talk about the specifics, what all will we be covering today?
Well, in today's objectives, I kept it a little bit narrow. I want our audience to understand CoolSiC, which is Infineon's silicon carbide offering. We're going to cover an overview of this different silicon carbide generations because that can be a little confusing sometimes. I mean, what do we mean by Gen 1, Gen 1H, Gen 2, and beyond? And how has CoolSiC improved from Generation 1 into 2? Now, we're also looking to continue improving our MOSFET offerings with our .xt and topside cooled silicon carbide devices. So we're also going to talk about what's changing inside the devices with .xt and how do topside cooled devices really improve systems and assembly capabilities. And then we'll summarize it all at the end.
Excellent. Now let's start with CoolSiC. What do you think are the biggest advantages of using this solution?
Well, we've been using different switching technologies for decades now. There was silicon, then we had silicon IGBTs. Now we have wide band gap devices like silicon carbide and gallium nitride. But CoolSiC and silicon carbide in specifics has the ability to improve power efficiency. So it improves the efficiency of the overall system by reducing switching losses and conduction losses so we can more easily meet power efficiency mandatory standards. That's becoming more of a global thing. You see requirements from different government organizations requiring all of our power usage to go down or at least become more efficient. Now, moving to silicon carbide, we also get higher switching frequencies. And what this means is that as we increase the switching frequency of the device, we are able to reduce the size and losses present in what we call the passive components. So those are things like the capacitors and the magnetics and transformers around the system. With this improvement in efficiency and higher switching frequency, it means that the whole solution gets smaller, and this results in increased power density. So as we're trying to get the most power into the smallest space possible, we end up with a smaller size and weight design with silicon carbide, and we also, with that improved efficiency, get to reduce how much heat management we need. So that's the size of the fan, the size of the heat sink, we get to reduce the size of the PCB. Now, adding all this together, people think about silicon carbide as being a more expensive device, and that ends up not being true when we look at the total cost of the system. So we're able to reduce the size and cost of everything around the switch, reducing the overall bill of materials and manufacturing cost with silicon carbide.
All right. Now, Nick, before we talk about the specifics of silicon carbide, where does it fit in the general wide band gap ecosystem?
Well, in wide band gap, like I mentioned before, we have gallium nitride and silicon carbide being our wide band gap devices, and then the traditional silicon devices. Really, it differentiates based on switching frequency and total power. When you want to go fast, when you want absolute maximum switching speed, it's hard to beat gallium nitride. Gallium nitride has really enabled some new horizons in efficiency, power density, system integration, and it's good for like the 40 volt to 650 volt range. And then as your switching frequency gets above 100 kilohertz up into the megahertz range. Silicon carbide has a bit more of a wide spread of capability in applications as long as the switching frequency is staying below a megahertz. We see silicon carbide applications going from, let's say, 1 kilowatt or maybe 5 kilowatts up to the megawatt range. And these are applications that are 650 volts to now 3.3 kV or 3,300 volts and even higher. We're seeing potential uses of silicon carbide in 10,000-volt systems as we look to create a more efficient overall utility grid. And then silicon's still out there. Silicon's still a very good technology for a lot of mainstream technology in the 25-volt to 6.5 kV range across a wide variety of applications. But when you want maximum efficiency, you're going to start moving your system over to a wide bandgap device.
Excellent. Now, CoolSiC isn't new, right? It's had a couple generations, correct?
That's correct. So CoolSiC Generation 1 was actually released in 2017. So it's not what I would call a new technology anymore. It's been around for a little while, but it's continuing to improve. When you think about how long silicon has been around, we're looking at 50, 60 years of silicon technology now. It's had a long time to mature. Silicon carbide is still relatively young. And with that, we're just now getting through Generation 1, Generation 1H, which was a small improvement, and then on to now Generation 2. But I want to caution the use of the term generation. All it means when we talk about generation is specific to Infineon. This is our second generation of silicon carbide. But if we tried to directly compare to our competitors with their generations, it's not always fair to say this generation 2 lines up with their generation 2. So I would hesitate on that and look more at the device capabilities themselves.
All right. So, Nick, what kind of improvements were made between Generation 1 and Generation 2?
Oh, there have been so many good improvements from Generation 1 to Generation 2. We're now looking at enhanced switching performance and figure of merit factors. What that means is that when you design in our Generation 2 CoolSiC devices, you're getting 25% switching losses reduction, as well as a 10% total power loss reduction. We've also improved the internals in the device to help make the devices more robust. So it's our .xt interconnect technology that we're going to talk about more later. It means that there's a better thermal resistance inside the device, so we have a lower MOSFET temperature. Now, we also are specifying our RDS on at high temperature. This simplifies and optimizes the system design so that customers can work with our devices confidently and know how they will behave at actual operating temperatures. We have a best-in-class RDS on portfolio as well as a broad portfolio of devices, meaning that in our through-hole devices, we're getting down to a 7 milliohm device, and in our surface mount packages, you see an 8 milliohm device, but in the future, we'll have a 4 milliohm device in our topside cooled packages. One of the challenges of designing with silicon carbide is short circuit durability. It's less than a silicon IGBT, which has led to some challenges, but the Infineon devices, our Gen 2 devices, have a rating of 2 microseconds guaranteed. This means the system will be more reliable and able to withstand transient overloads more reliably. The overload operation, so as you're really stressing these devices, it's now rated up to a junction temperature of 200 degrees Celsius, so you can handle those overcurrent events as they happen. The parasitic turn-on robustness, so are these devices going to switch on when you don't want them to? Well, we've enhanced the reliability against Miller effect turn-on, so now we're allowing even more unipolar drive. What that means is a 0 volt turn-off gate voltage versus having to go to a negative turn-off voltage or a bipolar device. And now there's also a very tight VGS threshold and transfer characteristics distribution. This means that you have enhanced reliability and performance in paralleling operations. One device right next to his neighbor is going to perform more similarly than devices from our competition. Now, I mentioned the improvements of specifying RDS on at high temperature, and here I just wanted to lay out what that looks like versus some of our own devices. We have CoolSiC Gen 1, CoolSiC Gen 2, CoolGaN Gen 1, and CoolMOS. These are all Infineon devices, and versus CoolMOS, CoolSiC Gen 2 actually has a reduction of 33% in the RDS on value at high temp at 125 Celsius. Versus CoolGaN Gen 1, it's a 21% reduction in RDS on. Versus CoolSiC Gen 1, there's actually a 12% increase in RDS on at high temp, but that is played off of some of our other improvements in switching performance. So one thing I also want to talk about is figure of merit. Figure of merit is one method used in industry to try to compare devices in a specific application, but it's not always an easy one. You can't simply say this figure of merit is best for all applications. What you actually have to look at is figure of merit in an application because it can be different. With the first one, we're looking at what does a high efficiency, high power density system require? Well, for that one, we look at QoSS times R on. It's really enabling better soft switching. For example, a half bridge LLC where wide band gap leads to a higher efficiency combined with high frequencies. Next up is high power density. So if we're mostly concerned about high power density, then it's QG times Rn. This is about reducing driving losses, especially at light load conditions. It allows wide bandgap devices to reach higher efficiency at an increased frequency, which leads to an improvement in the power density, so size and weight reduction. Now, if we're looking at minimum switching losses in hard switch topologies, that's EOSS times Ron. So this is your classic boost PFC or inverter. And then if we're looking at like servers and onboard chargers, well, then we talk about QRR times Ron because it's a usage in topologies with repetitive hard commutations. That'd be like your CCM totem pole PFC. This results in a bill of materials savings for the highest efficiency. And then I compared our devices. So we're looking at CoolSiC Gen 1 and Gen 2, CoolGaN Gen 1, and then CoolMOS. Across all of those, we can see that we set CoolMOS as just the standard 100% value. So that's your standard that you're comparing against. With different switching applications, you can see the improvement in figure of merit really changes across applications. So I would encourage customers to make sure they're using the specifications that are relevant to their application.
That makes sense. Now, Nick, when it comes to switching, how do these two different generations compare?
Well, when switching, we talk about hard switched or soft switched topologies. In a hard switch topology, generation 2 sees a 10% improvement in total losses. That's a combination of conduction and switching losses. And this was in a system that was a 20 amp, 40 kilohertz system with a 10 ohm external resistor running at a junction temperature of 100 Celsius. And I want to emphasize this because too often we see devices tested at 25 Celsius, and 25 Celsius junction temperature isn't real. As soon as you start switching a device, it's going to warm up. So we like to test at 100 degrees Celsius junction temperature to get an honest reflection of what the part's going to do. Now, in a soft switch topology, the improvement is still 5% between Gen 1 to Gen 2 across conduction and switching losses. And this was a 100 kilohertz system, again at 100 degrees Celsius. So you can see in both hard switched and soft switched applications, CoolSiC Gen 2 really does allow for a noticeable improvement in power loss reduction.
So, what about unwanted turn on effects? How does CoolSiC deal with these issues?
Improving immunity against unwanted turn on effects is an important aspect of working with silicon carbide. We have something called a parasitic turn on or parasitic return on situation that can happen when there's an induced voltage on the gate that is higher than the threshold voltage. This can happen for a couple of reasons, but normally it's what we would call the Miller capacitance. And you'll see various ways to deal with this through like an active Miller clamp in the gate driver or external Miller clamp capabilities to try to stop this induced voltage on the gate to prevent the low side device from turning on. But if it's not handled properly, the PTO could increase your turn on losses or even result in device destruction because you may end up with a short through your half bridge. Now, the lower the PTO factor, the less likely it is to have parasitic turn on. It also means you get higher efficiency and safer implementation of a unipolar drive. You can drive with a unipolar power system instead of a bipolar gate drive, meaning that you can have a turn off voltage of 0 volts versus having to go to like -3. This is a simpler bill of materials, simpler implementation, but you can also drive the system harder without worry about the device turning on accidentally. Now, both at 1200 volts and 650 volts, we show excellent immunity against PTO. In the graph here, you can see reported as an example a 650 volt SiC MOSFET comparison of the PTO factor. So CoolSiC Gen 2 is the lowest PTO factor out of all of the devices there. And what we're looking there is the QGD at 400 volts versus QGS at VGS switching threshold at 25 Celsius. Now, this is calculated from the data sheets, and the graphs report the best devices amongst all the ones we analyzed.
All right. So, let's also talk about .xt. What benefits does this bring to the table?
Well, .xt is really about improving the device internally. It's designed to improve the device lifetime by directly addressing some common failure modes. And it's also led to direct improvements in the thermal resistance and cycle life of the devices. So now we're looking at silicon carbide plus .xt, resulting in extremely robust silicon carbide devices from Infineon. One of the most dominant failure mechanisms we see of standard joining technology is bond wire liftoff, as well as chip to substrate joint separation. This can really compromise a device and reduce its overall lifetime. And if you lose your MOSFET, well, your device just isn't going to work anymore. You're going to see total system failure. So, making the MOSFET as reliable as possible is essential to total system reliability.
Nick, you mentioned the improvement of thermal capabilities with the .xt, so talk to me about that.
Absolutely. So historically, we have a standard interconnection that is a soft solder joint between the CoolSiC chip and the package lead frame. It's usually with some sort of a J alloy. You can see the thickness there under the standard interconnection. It's pretty thick. Well, with .xt, we've moved on to diffusion or sintered process depending on the device. This results in a much more thin, uniform connection between the CoolSiC chip and the package lead frame. In picture B there, you can see almost the elimination of the solder joint through this improved die attachment. This means when you're able to go to a diffusion or sintered connection, the thermal performance in the small form factor improves dramatically. So at standard soft solder, we see about 0.68 Kelvin per watt RTH value, and there's something of a 27% reduction of that to zero point 0.5 Kelvin per watt in .xt. There's also less thermal resistance in getting the heat from the CoolSiC chip out to whatever your heat sink might be, and then the max thermal impedance at 1 millisecond moves from 0.28 Kelvin per watt in standard soft solder to a 35% reduction of 0.18 Kelvin per watt in .xt. All of this means that heat gets out of the chip more quickly, more easily, and more reliably.
So, Nick, explain to me the difference between .xt joining technology and standard joining technology.
Our standard joining technology was all about getting the silicon carbide chip attached so you could get power through it and out of it efficiently. Historically, this was done with an aluminum bond wire and then our standard chip soldering to a standard system solder base plate. These were again aluminum bond wires, chip soldering, and standard system soldering. Now, moving on to .xt, we're changing from an aluminum bond wire to a copper bond wire in some devices. This reduces the impedance getting power through the device. We're now moving to that diffusion or sintered interface that I mentioned earlier, and then we're doing a high rel system solder. All of this results in a more robust connection between the chip and everything going on outside of the device, and allowing it to get the heat out better, to get power through it better, and just to be overall a more robust and more reliable device in the system.
All right. So, Nick, do you have any real world examples of CoolSiC in action?
Yeah, thankfully, we've had the opportunity to use Infineon's CoolSiC in partnership with Siemens Mobility and Stadwerk München in a test pilot of the Avnio streetcar. This was powered by our silicon carbide technology and covered around 65,000 kilometers. The real results from this change from an IGBT module to a silicon carbide device reduced energy consumption by 10%. And on top of that, there was also a reduction of motor noise. Now, we always think about just straight system efficiency, but when using electric devices and electric motors, the noise of the system becomes important in the acceptance of it. If it's loud and whining and has that like old power tool sound, people aren't going to like it. But by moving to silicon carbide from silicon IGBTs, they were able to reduce the motor noise and improve the acceptance of fully electric street cars.
Very cool. So, let's briefly also talk about the evolution from through hole offer to SMD devices.
Through hole historically has been the way you use a MOSFET. The TO247 package moving from a 3 lead to a 4 lead, improving your device capability. Now we're looking at our through hole devices have robust thermal performance, but the downside of it is they're very manual. The installation and soldering of it means that it's a manual, usually expensive process, slow, and potentially has issues with reliability from just repetitiveness of the process, and humans have to touch it. It's also lower pin count. A standard TO247 device, a standard through hole device, really tops out at 4 pins, meaning that you have to get all the power into and out of the device through 2 of those pins, and then you have a gate pin and a Kelvin pin to improve efficiency. Now we moved on to a surface mount device with bottom side cooling. So this allows you to now go to fully automatic handling. So you don't have to have people in the process anymore. You can go through reflow soldering. You have a high pin count now, so you have more ability to get a nice low induction connection into the device, as well as getting more power in and out of it. But you have to heat sink through whatever PCB you're using, whether that's FR4 or you have sometimes a like a copper slug. Or now we're also moving on to SMD devices, but topside cooled. So no longer having to worry about cooling through the PCB. You could get excellent thermal performance, more similar to a through hole device, but you get the fully automatic handling and you get a high pin count that you'd get in a surface mount device. So it's kind of the best of both worlds for high performance and ease of assembly. Now, looking at a couple of our different packages in topside cooled, we have our QD pack, Tolt, and Tolt high voltage packages. These are all JEDEC registered, so we see other people making devices in these packages, which is exciting. It's nice for us to see them being accepted, especially the Tolt package has seen quite a few other suppliers working on it. But one thing that we've done is we've made sure to standardize across a 2.3 millimeter package height. This doesn't sound important initially, but when you're dealing with topside cooled devices, now you have a heatsink that has to span across the board. Having everything in the same height package actually allows you to heatsink all of your diodes, your high voltage MOSFETs, your low voltage MOSFETs, all onto the same cold plate with an isolation layer. So you don't have to have expensive machining to make a multi height heatsink. You don't have to have multiple heat sinks on the board, resulting in more assembly challenges. So, topside cooled with matched package heights makes it for the easiest assembly out there.
Fantastic. Now, Nick, besides the thermal advantages, TSC SMD packages also have manufacturing advantages as well, right?
Yeah, I mentioned that a couple of times that we moved from a manual process with our through hole devices to a very automated process with the surface mount devices. In the real world, we see the simplified assembly reducing the number of connectors by 76%. So that's a nice bill of materials reduction. You don't have to worry about stacking different boards. You have one big FR4 PCB that has all of your power components, all of your ICs, drivers, magnetics, and then you get a system cost optimization. So without having to do any manual assembly, we see a reduction in assembly costs of 33% and a reduction in the cost of the PCB itself of 18%. So you get a faster, highly automated manufacturing paired with lower assembly costs. And these are key benefits from the Infineon topside cooled CoolSiC offering. Now, when a customer actually wants to implement CoolSiC, we have a wide portfolio of devices from our Gen 1, Gen 2, and more Gen 2 devices coming in 2025. You'll see that we have in our through hole devices RDS-ons down to 8 milliohms, and these are good for systems up to like 50 kilowatts, but all the way up to an RDS-on of 234 milliohms. And why do I mention the high end? Well, there's more applications for silicon carbide than just the ultra high power stuff, but you also have to have devices that function off of the auxiliary power supplies. And what I'm talking about here in an aux power supply is it has to run from, say, an 800-volt DC bus that you would find in an electric vehicle, and maybe you need a 12-volt or a 48-volt system off of that. Well, your MOSFET still has to be able to handle the 800 volts, but it doesn't have to push 10 kilowatts of power. It may just be 100 kilowatts. CoolSiC in a higher RDS-on value is perfect for these aux power supplies. In our CoolSiC Gen 2 that's coming in 2025, you see up there the QD Pack half bridge. This is going to get down to a 12 milliamp device in QD Pack half bridge. This we actually have two discrete silicon carbide dies inside of the package, so you get a half bridge in one simple surface mount device. Then our standard QD Pack is where we're getting down to 4 milliohms in a single device. RDS-ons keep going lower, enabling higher efficiency systems and higher density power systems.
Nick, if my audience wants to get started using the CoolSiC Gen 2 MOSFET in their next design, where should they start?
Infineon.com has a wealth of resources for getting started with silicon carbide, whether that's CoolSiC Gen 1, Gen 1H, or Gen 2. But specific to Gen 2, we have coming some neat reference designs like our 3.3 kilowatt CCM bidirectional totem pole PFC with our CoolSiC 650 volt devices. This is a really high efficient device, so it's 99.2% efficient with high power factor of 0.95 at 230 volts AC. It has a really nice high density design as well at 72 watts per cubic inch. This is a nice example of how you can use CoolSiC in a totem pole. Now, if you want to go a little higher power, we also have a 5.5 kilowatt three-phase LLC converter with our CoolSiC Gen 2. This one is a maximum power output of 5.5 kilowatts with a peak efficiency of 98.5% and a power density of 120 watts per cubic inch. It's again using our 650 volt CoolSiC Gen 2 devices, but it also shows off our 80 volt Optimos. It has our EIS driver and a quasi-resonant CoolSet device, as well as all being controlled by an XMC 4400 32-bit microcontroller from Infineon. So this shows, again, a nice high density, high efficient, high power Infineon solution for power needs of the customer.
Fantastic. All right. So, Nick, can you recap your main points for me?
Absolutely. So in summary, the CoolSiC Generation 2 MOSFETs enable the accelerated design of more cost-optimized, efficient, compact, and reliable systems through a couple of mechanisms. We're enabling very low power losses in both hard-switched and soft-switched topologies, even versus our Gen 1 devices. We're improving the thermal performance with our .xt advancements inside the package, making the systems more reliable. We're raising the bar for the power possible in an SMD package with our new topside cooled devices. You don't have to go for a through-hole device anymore to get the best thermal performance. You can now use Infineon's topside cooled devices to get a lot of power out of your system while getting the advantage of simplified assembly. We've had an extended driving voltage range, so our VG threshold and VG capable of the device has extended higher, so you get more durability. We're making use of a trench technology in our MOSFETs for combining the performance with reliability and meeting the most stringent requirements. And we're also offering the most robust roadmap in the market, inclusive of package innovation. So going from 4 milliohms all the way down at the lowest RDS-on up through the higher RDS-ons that are worthwhile to have in aux power supplies. The CoolSiC Trench MOSFET design helps to drive sustainable competitiveness for energy efficiency today and in the future.
Fantastic. Well, Nick, I think that's all I have time for today. Thank you so much for joining me.
Thank you, Amelia. I appreciate the opportunity to talk about Infineon's Generation 2 CoolSiC technology.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Infineon. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.